Hello, everyone. Welcome to the Symposium on Shortcut Circuits for Vision in Development, Adulthood, and Rehabilitation. My name is Marta Garrido, and I am the chair of the symposium and also a speaker, together with three other wonderful speakers. The first one is Marco Tamieto from the University of Torino in Italy. The second speaker is James Bourne from the NIMH in the US. I am the third speaker, and the fourth speaker is Sarah Agina from UCL in the UK. Before I get started, I'd like to acknowledge that I am speaking from the indigenous lands of the Wurundjeri people of the Kulin Nations. I pay my respects to the elders past and present, and I extend those respects to other indigenous peoples who might be listening today. I also acknowledge that the lands on which we are, or where I am today, have been a place of discoveries and knowledge sharing much before the university was established. So I will now move on to my talk, and I'll say that all of the talks that we will hear about in this symposium are very much inspired by a fascinating phenomena of blind sight. And blind sight is a remarkable phenomenon whereby people who become blind after an insult to their primary visual cortex retain, nevertheless, visual abilities that include things like detecting motion, being able to navigate through space while avoiding obstacles, or even detecting affect. And what I will show today is evidence for pathways that might carry that information, which bypass the visual cortex, but I will show this in a normative population. But I'd like to first start by showing you some of the incredible images of the brains of one of these patients with blind sight. So this is TN. It was described by Beatrice de Gelder back in 2008. And in this case, this patient had bilateral lesions of the visual cortex and yet retained amazing abilities like avoiding obstacles while navigating through space, and also was able to accurately detect, discriminate affect in faces that he could not see. And that has been described as well by Beatrice de Gelder and Alan Pena before. So this is incredible, right? So there's no visual cortex. People can't actually see, and yet somehow they can use that information correctly. So they are somehow perceiving, but without seeing. And the question is how? How is this possible? And I think the answer is the brain finds a way, but how does it find a way is what is very puzzling and very exciting to me. So one possibility that has been put forward to explain blind sight is that perhaps there are shortcuts that bypass V1. And so when V1 is damaged, somehow still the information gets to where it needs to be and is processed in a way that is useful for the person without needing to rely on V1 processing. And here I've got an example for the case of motion detection, whereby two alternative pathways have been proposed. These are the major ones that have been proposed. One that says that the information goes directly from LGN to V1 LGN to MT or V5 bypassing V1. The other possibility is that the information goes from pulvinar directly to MT, again bypassing V1. So the question really is, are these two pathways operating simultaneously? is one more likely than the other? What is going on? I'd like to show you some evidence for both of these pathways. There's more that I could show, but given the time limits, I will just focus on two key studies that I selected. And one is actually from our fourth speaker, Sarah. And she and her team showed in people with unilateral damage of the visual cortex, some of whom were had line sight abilities and others who did not. And what they showed was that for using diffusion imaging, for those who did not have line sight, the fractional anisotropy between for the damaged hemisphere was a lot smaller than for the intact hemisphere. So there was a big difference between the two hemispheres for those who do not retain visual abilities. However, for those who do retain visual abilities despite a big lesion in the visual cortex, the fractional anisotropy is very similar between the intact and the damaged hemisphere. And the same pattern is seen for mean diffusivity. So these data seems to suggest that perhaps is this pathway, the integrity of the pathway between LGN and MT for the blind sight positive patients that might enable these blind sight abilities that remain. Of course, there's evidence for the pulvinar pathway on the other hand, and one of the key studies comes from our second speaker, James Bourne, and what he showed was in one patient who became blind at birth. Again, using diffusion imaging, he showed that the number of tracts for LGN to MT was actually quite a lot smaller than for the controls. However, for the pulvinar to MT connection on the left side, there were actually a greater number of tracts compared to controls. And that data seemed to suggest that perhaps this increased connectivity between pulvinar and MT is what enables the blind sight abilities despite a big lesion in the visual cortex. So who's right? Possibly both, and there's different reasons for why that might be the case. Time of insults in relation to development, individual differences. There could be a number of different reasons, but we thought it would be interesting to see what do these pathways look like at baseline. So before there is any insults in the normative population, before any neuroplasticity happens as a consequence of the insult. So what is the starting point for a normative population for these pathways? So to do so, we took advantage of the Human Connectome Project dataset, which has been an incredible resource, and we took the data that was acquired at 7T, and we called that our discovery set, and we also used data that was collected at 3T, and that was our validation set. So when we exclude all the twins and so forth, we have a sample with 98 people for our discovery, and our validation set has 381. This work was led by a former postdoc in my lab, Elise Rowe, and I think she did an amazing job, and you've got the link for the preprint there as well. So what we did here was to look at these two pathways, pulvinar to MT and LGN to MT, and we used diffusion-weighted imaging and tractography to try to reconstruct these pathways in all of these individuals. And we were able to do so for both pathways, pulvinar and LGN. You see pulvinar pathways in purple and LGN pathways in green. for the 7T on the left, and then replicate it for the 3T data on the right. For most people, we were able to reconstruct these pathways. And then what we looked at was both the streamline count and the parent fiber density for these pathways bilaterally, so left and right, and again, for LGN pathway, the MT pathway, so LGN to MT, pulvinar to MT, and for 7T and 3T. So when we look at all the data to put together, what we see is that there's actually a greater number of streamline counts and also greater density for the pulvinar pathway compared to the LGN pathway. When we looked a bit more in detail as to where within the pulvinar these streamlines go through, we saw that was mostly consistently within the inferior pulvinar. So that is interesting, but we then thought we asked something further on top of that, which was, what about myelination? Because one of the reasons why this idea of the shortcuts gain some traction is that having shortcuts will increase speed. These pathways can be shorter, and so the information gets the information that is, especially the information that is critical to survival, will get to where it needs to be in the brain a lot quicker than going through the traditional pathway, the cortical pathway, through V1 and then through all the cascade of visual processing until eventually the brain can respond appropriately to that information. And so in thinking about speed, we thought, okay, well, for these shortcuts to really be useful in providing faster information as compared to the V1 route, then these pathways should be heavily myelinated. And so we asked, what does the myelination look like for both of these pathways? And again, the same approach, looking at our discovery set in the 7T and our validation set in the 3T, both pathways, LGN and pulvinar, left and right. So what do we find there? And I should say, for myelination, we use the T1-T2 ratio. We looked at the myelination along the tracts that we reconstructed from the previous step, from the diffusion imaging data, and then we averaged the myelination through that pathway in order to have the final estimate for each individual participant, which you see in the bottom graphs on C. And so when we look overall at these tracts, then we actually find that the LGN pathway is more myelinated than the pulvinar pathway. So in sum, what we found was greater fiber density for the pulvinar pathway, but greater myelination for the LGN pathway. And it seems to be somewhat contradictory, and initially I didn't actually believe that was the case. But what we interpret is that perhaps the LGN pathway to MT is used more so than the pulvinar pathway in adulthood, and this seems to suggest that perhaps there is an adaptive myelination for this pathway that leads to presumably to faster signal transmission. So of course, one of the limitations of this study is that we only look at anatomy. We don't have a behavioral measure of whether people's responses really are faster the more myelinated these pathways are, and that's definitely something that we are following up on. So just to conclude, I think this study and many other studies that we see today in this symposium and beyond demonstrate that the brain has shortcuts for information information that is critical to survival. Again, information about navigating through space, recognizing fear in the environment is also another example of critical information to survival. But the question is still why has the brain evolved with circuits that are in some way redundant in terms of the types of information that is being processed in parallel to the mainstream route, which in the case of an insult ensure redundancy, which is a great thing and important for adaptation. But then also the other possibility is this idea of increasing speed. So shortcuts are shorter pathways, perhaps more myelinated. But again, that's something that we would have to compare to the myelination for the cortical route, which we haven't done. And the other possibility is that perhaps these shortcuts ensure efficiency. We discussed actually these ideas in a review paper, which I invite you to have a look at. But one pressing question for me is that we know that the brain is heavily connected, and at some level, all areas of the brain are connected, perhaps not directly, but indirectly they will be. And yet, even though this information reaches, like say in the case of blind sight, information about motion reaches MT, still information remains unconscious. Is still in this case a patient is not able to actually see, and that is a question that I often ponder on. So with that, I'd like to thank my team, and especially Elise Rowe, who was a former postdoc in my lab and ran all the DTI and myelination analyses. And also just a plug into a poster from my student, Arshia Sangoshuli. Please go see his poster. He will be talking about some of these, again, inspired by blindsight, but looking at different pathways and shortcuts in that can change through development. So thank you very much, and I'll look forward to seeing you in Montreal.